Well, welcome back, everyone. Looks like class has officially started. So for today's class, our major goal is to continue working through section 3.2, but also obviously take questions about exam one that you may have. Our first exam is going to be next class meeting. So for the folks who are in the online section, you'll have arrangements with the Pocatello Testing Center. There won't be an actual class on Zoom. And for the people in the in-person section, it'll be kind of like a normal day, except everyone's quiet and working. So kind of a strange day, but we'll get through that one on Monday. And as far as the information that we discussed before, still working on getting this file sorted out, all the solutions posted. I hope to have that done before we go to the weekend. But any questions at all, folks, before we get started with today's work? Okay. Also, maybe last parting comments talking about exam one are, if I was studying for the exam in this class, probably the very first thing I'd want to do is first, make sure I'm caught up on those sections specifically, since those are the ones on the exam. After those are caught up, get them sent in, I'll have them graded and returned to you. Even if you turned in these sections as a hard copy, watch for your ISU email address over this Friday and the weekend if the grading goes late, hopefully not. I'll be scanning your work and sending it back to you so that even if you send it in a hard copy, you'll get feedback on those sections. So then after that, take a look at the feedback. If you missed any problems here or there, if there's any comments, make sure you understand why you might have made an error or what the comment was trying to say so that you have all that information squared away. Then after that, the homework exercises are the most important part of the course for studying for the exam. But after you get all that squared away, then it's a good time to take a look into these other sections here and here. You may decide to try to solve all problems. I think that's fantastic if you have the time, but you also have to kind of balance the amount of time you have and the amount of studying you want to do. If you feel like one of those sections is a little bit more trickier than others, try to first zero in on that section using either one of these documents. Well, that's my advice for studying for the exam. If questions do come up as you're studying for this exam, whether it's even on the weekend, please don't hesitate to email. I always check my email as pretty much a ritual, routine, and a habit. So no matter what, I'll be getting back to you even on the weekend. But that was our spiel for going into the exam. We have to keep going forward in the course, so we're back to section 3.2. So here's where we left off.
Quick question.
We're discussing truth tables. Oh, sorry, go ahead. Question
So,
first.
I'm in the online course, I believe. I don't know if I'm designated as the online in the
Hmm.
online course, but I'm wondering if I was to show up for the in-person exam, I'm going to ask this for the 3350 class as well. Can I take the exam in person, and is it set to be during the normal class time?
Yes, absolutely. So for both of the classes you mentioned, you're welcome to come in person to take the exam. I made sure that I have additional copies, so that will work just fine. And it would have to be during the actual class time.
Okay, thank you.
Yep, absolutely. That's a great question as well. And kind of the spirit of my answer to that question is that even though it feels like we're separate classes, in spirit, not really. It's running concurrently. This is really one class. There's just different modes on how you're participating, online versus in person. And I have no qualms if the class kind of essentially cross-pollinates. If people in the online section come and sit in on an election in person, or if someone in the in-person section, maybe it's a snow day or something weird going on, if you have to use a Zoom link, participate this way as the online section, no harm done, even on an exam day. So even on exam day, I just have to be aware to print extra copies, but I made sure that happens. Other questions at the moment about either that or other exam topics? Okay, thanks for asking about that one. That's always kind of an important clarification. I usually get a lot of questions along those lines of, is it okay if I use the Zoom link, even though I'm in person? And vice versa, have questions along those lines like you were asking. And it's always totally fine. It'd be really weird to want to keep track of exactly how people are participating to somehow go after the students. I think that'd be a weird thing to do. So if you're here and participating, I always think that's just completely fantastic. So let's go back then to this section right here where we left off on Monday's class. Our major goal in example 3 is to construct the truth tables for our major logical connectives. They were the not operator, the and operator here, the or operator, and the exclusive or. And we got started with one of them. The not operator is not too bad to write down as a truth table. In fact, I kind of made a mistake when I first wrote this down, because usually you're writing down an assignment of truth for both P and Q, but this one is short and sweet. If P is true, the not operator converts it to false, and if P is false, the not operator flips it to true. So all it's doing is flipping the truth assignment. Well, the next most interesting one is P and Q over here. So let's try this one next. This table is a little bit more involved because we have to, again, as we said, give an assignment of truthness or falseness to both P and Q. So really what's going on here to start us out is it's a lot about just organizing this. There's two options for truth, false on P, same for two options on Q. So there's 4 different combinations of truth assignments on both of these propositions. So one way to strategize here is go like this. So here are the 4 rows under P and Q for the 4 possible options. And the organization, although you don't have to strictly follow it, I'd say it's a really, really good idea. I would always start personally by going true, true, false, false on the P column. Then on the Q column, we have to change the strategy to go, let's make this be, say, true, false, true, false. Then this would be all the combinations of truth assignments for both P and Q. Does that make sense there? I'm running through these here. Okay, if it was 3 of them, P, Q, and R, that gets a little bit more involved because now there's 8 rows, so that won't come up as much in class. But if it ever did come up, that would be a good way to kind of extend this sort of pattern into that new situation. Next thing we drag in is the operator we're investigating, P and Q. We were just defining these last class, so it's a good to always remind yourself when you see this, think and. Well, that means if it's the and operator, we would get true in this situation. This is when both P and Q are true, so the statement P and Q evaluates to true as well. But what would you all say is the response for this one? When P is true, but Q is false? Absolutely. The AND operator only evaluates to true when both P and Q are simultaneously true themselves. So one bad egg right here means the whole assignment is false for P and Q. On this one, even though Q is true, P was false, so we evaluate this one to false as well. And last, false to false gives us an assignment of false on this operator right here. So when we go to think about how to assign truth or falseness to larger compound statements, if P and Q ever come up, we have this table in the back of our mind's eye. In fact, the first few times you started working with these kind of operators, it's good to have this just kind of pulled up. Maybe flashcards and stuff like that is a really great way to absorb this kind of information. So that's the AND operator. Now we move over to the OR operator. This is the inclusive OR, so we have to be careful on how we write this one out. But the table starts off just as before. Let's put in 3 columns. Then 4 additional rows going down. This is a lot easier to do on paper, it turns out. I guess I have a shaky hand today. I blame the coffee. So first go P, then Q, and I put in a little too many columns there. Let me fix that one. P or Q. And same exact truth assignments, only because I want to keep it in a nice organized way. If I scramble these, sometimes it can kind of scramble what you're thinking about when you're doing this sort of evaluation. Maybe not so much on the or the and operator, but for other ones, it could cause some weird problems. It's good to be consistent is the short of it. So I'll go true, true, false, false. Then on the next one, alternate true, false, true, false. And this is where the operator gets a little bit weird it evaluates to true if at least one of the propositions is true or the other. If they're both true, it still evaluates to true. This one evaluates to true as well because we have truth assigned to P. But think about how weird these statements can be. If P is a statement that's true, like it is a Wednesday, and Q is the world's most absurd statement, like the moon is made out of cheese, still it evaluates to true. It makes no difference as long as one part is true here. It feels wrong, right? But that's what we're forced to say with logic. So now the next one, same idea, P is false, but Q is true. It has to evaluate to true. So the only way we get false is if both propositions have false assigned to them. So we would put false down on that one. So that's our OR operator. This was the not operator. And the last one with the funny symbol, anyone recall what that was meant to be? I guess it's up here on the notes. That's a weird question. This one was the exclusive OR up here on the notes. I'll use the shorthand, XOR. I usually say exclusive OR, but that's just a fast way to write it down. You probably want to have it kind of next to each other, so you're not seemingly saying X or something else. So now for the last one, let's put it right under the OR operator, just so we can compare. We'll go PQ, P, exclusive OR Q, several rows down below as before. Then normal pattern of the truth assignments, true, true, false, false, then true, false, true, false. Finally, we're all set. Anyone recall what the first one should be on this row? With both P and Q are true, in an exclusive OR, would that be a true or a false? It is false, absolutely. So this is one where it's trying to match up what people say in ordinary English. People might say, I'm going to the store or I'm staying home, and they're often meaning an exclusive OR. In that example, it would have to be exclusive. So this is where this kind of operation would fit in. This is false. It has to be exactly one or the other evaluating to true. So in this one, if P is true, yet Q is false, then we get a truth on this one. Vice versa, swap the assignments around to make Q true, P false. We get true as well. And finally down here, false to false would evaluate to false as well. So this operator here, you know, it honestly feels funny to me when you really look at the truth table. This one feels a little bit more natural, but again, once you bring ordinary humans English into the mix, this one does have its value. So that is the exclusive OR. Now, finally, with all these tables down, if we were going to look at some more larger compound statements and decide if those statements are overall true or false, we can use each of these four tables as a guide. That's what we'll be doing on the next example, but any questions first, folks, with the assignments here? Okay, well, actually, let me take a slightly different screenshot. That ought to work. Well, let's try this out down below. This is the part of the assignment that I was mentioning on section 3.2 where this kind of work was sorely missing. When you have all these new operators and you're just learning it for the first time, you've got to practice with that kind of stuff. And so I went back to section 3, assignment 3.2. I did fix the PDF on here. And this is what this homework assignment looks like. It's the same kind of things that we're doing in class, assigning truth and false or rating out statements. This is the missing stuff that wasn't in the exercises, but I thought these ones were good right here on page 93. So it's going to end on these fast questions right here, just writing out what the statement would mean, given this table down below. If you look at the rest of the exercises, it's not that they're bad, but they're highly, highly technical, not really getting at these. It's almost as if the exercises are written with it in mind that you had already done this kind of work right here. So let's give all this a try. We're told the proposition P is true, Q is false, R is true, And using that information, all we're going to do is assign either truth or false to these now compound statements down below. I'll go first. If we have not R, the R was assigned to be true, we would say that this is false. You don't have to say much more if you're doing this as an assignment, but it's good for the notes just to say why. We'll say it's false because R is true. And the negation operator, all it does is flip the assignment to false. So that's a pretty fun one. Next one is the or. Any volunteers for saying the truth assignment for this one? Should this be a true or a false? Good call. This one absolutely does evaluate to true. And that's because P was true. So we'll say is true. It doesn't matter what Q was at this point. The moment you found one proposition that is true, you're all set. The whole assignment with the or operator evaluates to true. So I'll say here just briefly, because P is true. And that's all it takes when it comes to the or assignment. Well, next one is the exclusive or. You need to be very mindful on what the assignments are for P. P is true, or is true. So this one is the weird one. This evaluates to false automatically. Exclusive or means exactly one has to be true in order for the overall truth assignment to result in true. So we'll just say here is false. Explanation on this one could be just simply saying because both. It's really all about both right here. P and R are true. So they go kind of fast once you have a good look at these. But how about this one? Q and R. Any volunteers for the assignment on this one? It would be false again, absolutely. The false on this one is because of the and operator, and only one false, either one or the other, Q is false in this case, is enough to make the whole thing false. So think of the analogy, one bad apple makes the whole thing false, is that what's going on here? So is false. Not that necessarily true or false is a good and bad thing, it just all depends on context. But we'll say this one is false because Q is false. Then last one, this one's really several operators all at once. So we have to think about what's the assignment on P, what is the operator, and what is going to be the assignment on not Q. Well, it is an and operator. If P was false, we wouldn't even have to consider anything over here whatsoever. But it's true, so now we have to look at what's going on with Q. Q is set to false, but that means not Q is true. So both propositions, this one and the more compound one, is true as well. Through the and statement, the whole thing is true. We can say here, just for a brief explanation, this is because both. Again, the both is really important in here, much like with the exclusive or. Both P and not Q are true. So that's our practice so far with those several new logical connectives. Any questions at all, folks, thinking about these kind of problems? Okay, well, we're definitely building towards something, but you'll notice some of the logical connectives that you see all the time in a mathematics course, really we haven't gotten to yet. That one is the so-called implication. P implies Q. And to me, that's when this stuff gets a little bit more vague and foggy. Our authors trying to help out with this table right here felt like it was a great one to bring into class. Because when we're dealing with the implication, P implies Q, this is when we're getting into situations where vacuous truth can happen, and that is extremely confusing the first time that you're looking at it. So let me first try to just scroll to the right spot here. So that operation right there is often read just simply P implies Q. Using more words, our author says this assignment, P implies Q, is going to be true when the truth of P implies the truth of Q. That's a really important statement that you have to kind of come back to and think about again and again. And in the reading, the author had a good take on this that I've never seen before. Think of P implies Q as a sort of promise that if P does evaluate to true, Q must evaluate to true. If that promise is violated, we say the whole implication, P implies Q, is false. But that has a big consequence. P implies Q is true unless P is true and Q is false. What they're saying here is there is only one way on the truth table for the implication to ever be false. It's when P was true and then Q came out as false. So that's a little bit tricky on this. We'll investigate how this all can be evaluated with these kinds of statements down here. But even before that, other interesting things you can say about P and Q. Oftentimes P in a math book you might consider to be the hypothesis, Q to be a conclusion. Less familiar words for me is P is sometimes called the antecedent and Q is called the consequent. Either way you say it, it's a powerful statement, but it's also extremely vague if you try to say it in ordinary words. For example, often when I write out P implies Q, this is going to be the default way I would just write it down. If P, then Q. But everything down below is thought of as an equivalent way to say this in ordinary English. Ordinary English is messy, imprecise. Some of these, it just doesn't even feel like the direction is going the right way. Seems like this is saying Q implies P when I read this one. That's meant to be all the same. So for me personally, when I write down problems, exam questions, homework problems, I'm almost always going to state it this way because I feel like it's direct, straightforward. It'd be the same statement. It'd be the same kind of sentiment of this one right here. This one says if you are a legal US voter, then you are an American citizen. But notice all those things down below are trying to convey the same kind of thing. Some of them might feel natural, some of them might seem kind of strange. They're all trying to imply the same sort of information. So think of this table as another way of our author trying to say English is imprecise. Anything you can try to do to make your statements as precise as possible is well worth it. So that's why usually for me personally, I always try to write down an implication statement in the most straightforward way. If P, then Q, whatever P and Q happen to be. So that's the introduction to the implication, but we really understand what it is once we see the truth table. For example, reading that is pretty technical and vague, but seeing stuff like this spells it out exactly what the truth assignments are, what they will look like. So we need to do another one right here to get a feel for that operator. Any questions first about the overall definition? Okay, let's start by writing it down then. Same kind of table as before. We have P, Q, P implies Q. Let me try a little bit better with that symbol. Several rows down below as before. Then just the standard truth assignments we've been putting down to build these tables. Okay, so here's where it gets interesting. Usually when you're thinking of a statement P implies Q, this is the one you're thinking about often. If P becomes true, Q must be true is what the implication is trying to say. So this row would evaluate to true. Let me just put a T here like the others. But this one is when it's very obviously false. If P implies Q is true, as a statement, we have a problem then, a contradiction whenever P was true, but then Q became false. So this is the one where it's just a patently false statement. And the next two down below are really very vague. recall up here in the definitions, P implies Q is true unless P is true and Q is false. This is the unless part of the table. Maybe we can put some highlighting here to match the gray above. So they're telling us by this part of the definition, next two entries are both true. And they often feel pretty awkward in a certain sense. These are sometimes, like we mentioned before, last two rows are called vacuously true. What makes them vacuously true is, on this one, if we have false, but this came out as true, well, the implication P implies Q was never violated, because the only way to violate this is, as they say here, have the truth of P imply Q go wrong. But on this one right here, P wasn't true to begin with, so there was no chance to violate the implication P implies Q. And same idea here, if false to false, well, no violation of P implies Q whatsoever. It's really kind of hard to think about it without context, so that's what part B is all about. But any questions at all, folks, thinking about this table so far? Okay, well, maybe just another thing before we go down to the example. These implications are the sort of things that get written down almost all the time in mathematics. For example, sometimes people format their work in this kind of way. 2x minus 3 equals 5. Well, that's a proposition. This proposition implies 2x equals 8, which would then imply x is 4, but let's just keep it with one implication. All this is saying is that if this equation is true, then this equation must be true as well. Then we can keep on taking it further with more and more implications. And so pretty much mathematics is just built on this kind of thing in a certain sense. But down below, here's the example to try tying what's going on with this truth table here, to try to make sense of the vacuously true entries down below. These last two being true, again, is always a real surprise, kind of a head scratcher, the first time you're introduced into this operator. So I have two propositions. P is you sing, Q is my ears hurt. So we have the proposition P implies Q is just rewriting if you sing, think of the arrow there as then my ears hurt. We want to investigate how this whole P implies Q is going to relate to these four assignments above, just to try to make sense of them. And if they don't make sense, well, we'll try harder to see if we can make sense of it. So let me know if something just seems not quite right as we go to list these out. I'll number these so we can relate them for the truth assignments above. So this will be for part 1. And the implication, if you sing, then my ears hurt. That's the P implies Q right here. This would be saying, you sing, my ears hurt. And this would evaluate as true in this statement here, because the implication P implies Q, again, is just thought of as our author says, a sort of promise where if P is true, Q must be true. So that's all that's going on in option 1. Option 2, or row 2 rather, on the truth table is saying, well, you sing, P is true right here. Then going off to Q, this one's set to false, which means we would say, my ears don't hurt. And I think a lot of people would agree that makes this false assignment make sense. The implication, if you sing, then my ears hurt, must not have been true if this outcome really happened. You sing and my ears are totally fine. So that's why we definitely put a false into that statement there. But the next two, again, get a little bit more vague. So let's try it out again, try it out all over again on the third row. So row 3 is saying this next. It's false for the proposition P. So we would say, you do not sing. Then over to the right, we're saying my ears hurt. But we still call this true. Anyone see a way to kind of rationalize why this would really be true here? Just copying down the true false statements that were on the right column of this table. Okay. Kind of a tough one to rationalize in a certain sense, but you know what you can think about on this one is here we're signing true to the statement, even though the statement is, if you sing, then my ears hurt. The person didn't sing, the other person's ears do hurt, but it's possibly because these were unrelated events in the first place. Maybe that person had an earache, for example. So true can happen here for unrelated reasons, not dealing with the full implication. So we say the whole statement down here would be true. Any questions with that down below, folks, thinking about this one? Okay, let's try one more then. For 4, what happens here is, well, you don't sing. For the next part on Q, my ears don't hurt. I think this one is a little bit easier to rationalize why we assign as true. And that's because the only way to falsify the implication, if you sing then my ears hurt, is if you actually have to sing to challenge making my ears hurt. Sorry, kind of had a micro sleep right there. So if you never did the P part, there's no way to challenge the implication to make it come out as false. So we just say the whole thing is true in this assignment down below. So that's the implication P implies Q. When we say P implies Q, oftentimes in our mind, we're thinking of just the 2 rows up here, which usually make the most sense. But there are other truth assignments that we have to rationalize. The ones down below are the vague and foggy ones. And again, it has a nice way to explain vacuously true. These are true by vacuousness because the proposition P never evaluated to true in the first place to challenge the implication P implies Q, forcing it false. So lots of ways to think about it. Writing it out in an example, again, is really important because you don't want to think about it purely symbolically. Tie it in with ordinary propositions that you encounter, and you can make these things a little bit more meaningful. But next thing we want to do is just practice with this new operator. So that's going to be our next example down below. So let's turn to that one. Oh, and it looks like I had a big revision on this one. In the original notes, I felt like I wrote this out in just a really awkward way. The proposition that was P was really a compound proposition, which is not in the spirit of what you would want to do for something of P implies Q. So I revised this whole thing right here. It looks kind of jarring with it all in red. Let me just put this part back to black. And that was the revision on this notes that was just this afternoon. Sorry if you've already downloaded it. So with a change here, this is just a carryover definition from our section 2.3 on set theory. The review here says, if A is a subset of B, we'll write subset equals, or if we know it's a proper subset, we'll take that horizontal bar off. But what it means is, if X is in A, then X has to be in B, and this has to apply for all elements X in A. We can define new propositions. P is the proposition X is in A. Q is the proposition X is in B. And so using those, this whole statement right here could just be rewritten as symbolically. Well, it was symbolically over here, but more condensedly symbolic. P implies Q. So now we're going back to this weird statement that we encountered back in our section 2.3 on set theory. We were told if B is in a set, it must be a subset, or excuse me, the empty set must be a subset of it, no matter what the set B was, even if B is the empty set itself. So it's also true that the empty set is a subset of itself. You have to use that subset equal bar right there, that like we discussed in section 2.3. So our goal is to show that that's true. How do we start? We have to just follow the trail led by the definition. The set A right here is playing the role of the empty set. So when we check the proposition X and A, we're doing this right here. Let's say step 1, consider P, X is an element. We say of A up here, but A is playing the role of the empty set. And that's our statement to start. But this statement, it is a proposition. It's patently false because the empty set itself has no elements. It makes no difference what X was. X can be a set, it can be a non-set, just an ordinary element. This would always be false just by the nature of the empty set. So we can say down here, step 2, the proposition P is false. There is no element in the empty set whatsoever is what we're stating here. Then we go to the larger statement. We're trying to show the empty set is a subset of this step B, whatever it was. That means back over here, we're wondering about the truth of the assignment P implies Q. Let's pause right here and think about that one. The statement P implies Q is true. Notice how strange that feels in a certain sense. The way we get that P implies Q is true is really just through this truth table right here. And in this truth table, let's just put it here for an extra visual on what's going on in this strange problem. In this truth table, we're on this row. P has evaluated to false. We don't even know what's going to go on with Q whatsoever. But whatever P is, if it's false, no matter what, the truth assignment does not depend on Q whatsoever. We're going to output an assignment of true immediately. So the statement P implies Q is true, but we want to say here, just if we want to be specific on the kind of truth, this is true vacuously, because the condition P had no chance whatsoever of being true. It was guaranteed as false. So in step 4, we make a conclusion. You don't have to read these out as steps 1 through 4, but sometimes it's nice to see this as a step-by-step way to reason through all this. In step 4, we'll say for the conclusion, therefore, the empty set must be a subset of B. Because the implication P implies Q, that's all we had to show, it's true. So again, this is just a weird statement. It's weird because its truth was only by vacuousness, but it's also pretty much the foundation of set theory. This is a very, very important statement. Without it, certain things like even probability start to have humongous problems. Well, any questions at all, folks, with this another look at the empty set? Okay, well, the whole goal with this one was to get a new look at what P implies Q is really doing in a more of a mathematical setting. But returning to more of the normal kind of things we're seeing in these notes, we need even more logical connectives. The downside with this arrow is that it goes one way. We would love to reverse this condition or make it go both ways. Making it go both ways is the so-called if and only if, which is surely something you've probably read a lot of in math books, the if and only if operator. Our author even has some comments on this. It turns out if and only if is used so often that a number of years ago, not too long ago, but I think it's over 10 years, if and only if, as a shorthand, has been entered into the Oxford English Dictionary as a bona fide word now. So that's thanks to the logicians and mathematicians and computer scientists, you could say. This is a great operator. Sometimes it's thought of as logical equivalence. P will be logically equivalent to Q if we put in this double arrow here for if and only if. Well, this is going to be true when both P is Q and Q is true. It's going to be false when both P is false and Q is false. So that's our logical equivalence there, or the if and only if. Any questions about it so far? Okay, another thing to mention that this operator here, sometimes it gets chained into huge statements. Sometimes you can have a statement that goes P, if and only if Q, if and only if R, if and only if P. Kind of in a circle. It's not exactly circular logic, it's just the same statement over here. You can have logical equivalence through several statements at once. And to just pause here for a moment, if you've taken linear algebra, here's a statement with logical equivalence that you've probably encountered. So just a slight pause in the notes to show that. It's in here somewhere. There we go. Let's go to this one. Characterizations is a way to say huge statement of logical equivalence. And this right here is just a whole bunch of if and only if statements, where it says all statements are all simultaneously true or all simultaneously false. That's the nature of the if and only if operator that we were discussing. So in linear algebra, this is a huge set of conditions that are logically equivalent, much like the three that we were trying to put down here, but imagine a whole bunch more. Like we said, in this, all statements are either simultaneously true or all simultaneously false. In our notes, we say P implies Q is true when all statements are simultaneously true. They're both true or they're both false. So essentially, if you have just two statements here, not too different than a huge characterization theorem that could be many, many statements, or maybe just a few like in this diagram. So if and only if plays a humongous role in mathematics. Not that it's more important than P implies Q, but it's powerful whenever we have logical equivalence like this. Because when it comes to P implies Q, you cannot reverse the arrows, but this one you can. So the truth table for this one is not too bad to build. Doesn't have the same issues of vacuous truth like P implies Q, thankfully. So it goes P, Q, P, if and only if Q. Then finally, let's build out the rest. True, true, false, false, true, false for Q. And logical equivalence says P if and only if Q will only evaluate to true if the assignments of truth are identical or the assignments are false are identical. So we'll have true to true here, but false everywhere else. So that's the P and if and only if Q. Any questions at all with this one, folks? Okay, well, let's keep on going next then to example 8. Purpose of example 8 is now to do something we did similarly before. Depending on the truth assignment of Q, this one's true. R, that one's false. And let me fix the spacing on this, didn't think that through. You really kind of want that all in one line to make it more readable. S is false. And I forgot proposition P. There's 4 of them this time. So like we did before, we're going to look at the statements below, decide which ones must be true, which ones must be false. You don't have to explain your work for these kind of questions, but I'll add that to the notes just for extra clarity as we're doing these. And I'll leave these up to the class. Now that we've practiced with all these different kinds of operators, Let's go through these one at a time. This one is not Q if and only if S. How about someone for Zoom on this one? Anyone see what this should be? True or false?
True.
I agree with you. The if and only if requires a match on true to true, false to false. Q was true, but the negation of here is false. S is false. And so, like you said, this automatically evaluates to true. We'll put down here, the explanation is because not Q is false and S is false. Again, these operators are kind of easy to kind of get mixed up in your head. It feels weird to say true when false and false came up, but that's just because the if and only if is just looking for logical equivalence. False to false will evaluate to true. Seems weird at first until we get the hang of it, but that's the purpose of these small exercises right here. Now, next one is the implication. We have to be very careful with this. There is only one way to make that false. So if you're a gambling person, true is a safe bet, but this is not necessarily random, so we probably don't want to bet on it. Let's look at the evaluations. R is false. S is false. So what would you all say this one should be? True or false? It is true, good call. This one is vacuously true, one of those uncomfortable ones, but it is absolutely true. We could say here the truth of this was because, well, when you really think about these tables, it's got to be true the moment we said R is false. Let's go look at the table again. It's way up here. When we say, well, the R is going in the P column, that's a little tricky, but the moment we say false, we're kind of shoehorned into a true statement right here. So that gave us that guarantee of truth, right? Or true here. And our statement could be because R is false. And we don't have to say it a single bit more. The truth of S, whether it's true or false, would still evaluate to true here just because of R. Well, be careful if R is true, then that one does depend. It could be either true or false, but this one's a guarantee. Any questions with those two so far? Okay, well, how about for this one, for really anybody? Would you call this true or false?
True.
Let me double check. Looks like this is the one that would be the one false for the implication. But you know, it's really kind of tricky on these. This one would evaluate to false. And that's because, think again of our author's way of thinking this. R implies P is like a promise that if R is actually true, the statement here is R is false, then, oh, hang on here. Not too sure what I was thinking about on that one. Sorry, I got a little bit mixed up on that. Based on the comment that we said above up here, this one would have to be true. Absolutely right, Michael. I think I just got in a little logical loop on that one. This one is true. Let me put an exclamation on that one. I'm not too sure what I was thinking on there, but maybe I was thinking P is true, R is true. Who knows? But back to on track on this one. This one is absolutely true. Once again, it's all about R. I had everything lined up. I forgot what I said just a line earlier. Because R is false. Again, watch out for those. That one tricked me this time. R being false in an implication automatically is going to evaluate to true no matter what. Well, let's try out the next one down below. This one's a little bit more trickier because, well, we've got a compound statement on the left. We have the if and only if, the double conditional in the middle. Another big compound statement on the right. So this might be a good one to just break down slowly. Let's first think about the truth of P and R. Well, P is true, R is false. Because that's an AND operator, the whole thing right here would evaluate to false. Next is R, exclusive or Q. Well, R is false, but Q, that one's true. So that means that in the exclusive or, we want exactly one of the propositions to be true. That happened here. So we have true on this one. Then that looks okay so far. We should be able to resolve the if and only if. But with if and only if, you need to match true with true, false with false. If we have a mismatch, well, logic does not go both ways in this sense. We have false for this one. And this is because we require both true or both false to obtain true in a if and only if connected. That was a longer statement than I intended, but there it goes. So any questions, folks, on practicing these statements down here? This one definitely tripped me up on part C. Okay, well, last part of the notes is taking a look at just a couple more of these kind of problems, writing down statements in ordinary words for this one based off 3 different statements here. Here, we're not really as concerned about saying whether these are true or false. We're just working with the operators in a different way by writing them out based off the propositions. So we have propositions P, it's winter, Q, it is snowing, R, the neighbor is mowing the lawn, and here we're just trying to write all of these out in ordinary words. I'll go first on this one. If it says not R, we would go to the proposition R and just say, if, forgot from this statement right here, I'd want to lead with an if and then when I would write this out in ordinary words. So go if the neighbor, and let's see, there's no spell check in an equation field, so these things have a habit of cropping in. That said, that, I don't even know how you pronounce that. Let's remove that consonant. Sorry for the distraction there. If the neighbor is not mowing the lawn, the not operator or the not statement here came from that operator, then the if then in the problem came from the implies conditional right here. We'll say then P, it is winter. So that's all we're doing on this kind of problem right here. Does that make sense to folks on writing out this statement? Okay, really it is a lot to kind of absorb on these notes, which is tricky because the problems go fast, but there is a lot of information here. So these are good problems to practice quite a bit. And that's why the homework exercises, again, had those extra problems, not in the textbook, to just support this kind of material. But let's try this one out again. This is P, following the color coding, if and only if Q. I don't have color coding on that one. This one would just be saying right away, it is winter. For the biconditional here, we'll say if and only if. And if you wrote out this, that would be okay. That's, again, in the Oxford English Dictionary, so it's an appropriate shorthand. But I did think the author was really interesting when he said he will not be using this. So he's taken a stand. He does not like the shorthand. You won't see it in the textbook other than the one time he mentioned it. But that's just his opinion. It's all up to you how you would like to stylize your write-up. I usually do agree. It's sometimes nice to just write these things out for extra clarity. So I'll go this route as well, like the author. So it is winter, if and only if. Just read out the statement Q. It is snowing. Obviously, that doesn't apply to Idaho right now. It was really nice weather as if we were in, say, April. But that's all the statement is trying to say. We're not as concerned about the truth or falseness of it. We're just reading it out. They get a little bit worse over here, but just a couple more to get through. Any volunteers for reading out part C? This one's kind of bad in a way, right?
If it isn't winter or snowing, then it's the neighbor's normal one.
Yeah, that could work, depending on how you're meaning, because that operator right there can flip this whole thing into, I believe this is how you're saying, not P and Q becomes not P or not Q. We're going to see these kind of statements down the line. This is one of De Morgan's laws of logic. And yeah, that absolutely works for this. So let's read this out the way you said it. Let me see. So not P, just trying to collect my thoughts. That would be saying, first, I probably want to think about that operator when I'm writing this out and say, if, now I want to write out this part, the not P or not Q. So we'll say, if it is not winter, or for Q, it is not snowing, then, so the if then is only through that implication right there. Then R will say here, the neighbor's mowing the lawn. I would want to meet this guy after all these statements. He seems to have a very good work ethic with lawn mowing. Notice though, however, that this is like one out of a whole sea of different ways you could write this out. English is inherently imprecise. So when I read these out, I have to kind of be forgiving that you intended one of these sort of things, or maybe you were trying to write out this statement more verbatim as you saw it. So there's a lot of judgment calls on these kinds of things. I'm not going to be hyper specific to say you missed something here or there. If it has the right feel, if it sounds like something someone would say, and it does connect back with this, it would get full credit. Again, these are a lot harder. You probably had a different statement in mind. For me, I think when I practiced this one, I said, if it is not the case, because of that operator, that it is winter and it is snowing, then the neighbor's mowing the lawn. I used if it is not the case as a kind of parentheses to wrap around P and Q, but this is a clever way as well. De Morgan's laws for logic can give us a type of algebra when it comes to sets, to logic, but also sets. The complement of A intersect with B is equal to the complement of A union the complement of B. We mentioned before that logical operators and set theory operators have this eerily similar algebraic structure. There is a thing called an isomorphism between the two if you specify it just right, where if you look at these symbols, it's hard to tell if you're doing set theory or if you're doing logic. They are all working exactly the same. The only difference is how we're writing them. So that's a kind of interesting tie in with set theory, but that's kind of not here or now. Let's work out part D on this operator here. I find that one's pretty challenging to write out as well, even though we usually imply an exclusive or an ordinary language. Any volunteers from the class on how to write out this one? It's tough because we can't, in this situation, say it is winter or the neighbor is mowing the lawn, because then we're talking about potentially an inclusive or. You have to say something that really directs it as being an exclusive or. So something in English will give us those tools, but there's more than one way to really imply this. For me, if I had to do this one and I want to make it an exclusive or in spirit, I'd probably go like this. From that symbol alone, I would begin by saying either. Oftentimes when you see either this or that in English, you're trying to imply an exclusive or. So that's what I would start with. But that's not always the case. It just depends on what the person is meaning. So if you're being really hyper careful, you might add even more details here. So I'll go either P, it is winter, or R, the neighbor is mowing the lawn. And if this was a response on, say, a homework assignment, oh, hang on, let me fix this. If this was a response on a homework assignment, or I guess I can't fix it, or maybe a response on an exam question, I would say that that would work for full credit. But again, if you want to be super, super specific that this is an exclusive or, you might say, but not both. And that's a great catch-all to really emphasize the exclusive or was working on this one. Let me see if I can put a border here. No, that doesn't work. Oh well, we'll live with where this ended up. But any last questions, folks, on getting through these statements here? Okay, well, looks like this material went a lot faster than I had intended. So let's do one more exercise that's going to connect with the next section, and then we'll call it a day, or take questions and then call it a day. Last thing I want to investigate is this statement that was written down here, not the one above, even though it's essentially the equivalent statement in the land of set theory versus here, the land of the propositions. But one way you can really think about what's going on with this is you could write out another truth table. It's going to look like this. We'll go P, Q, put down some assignments. Standard assignments are true, true, false, false, true, false, true, false. Now let's break these down. First, we want to work with the operator P and Q. For the operator P and Q, we need to put down the assignments to understand this entire statement over here. So first, we'll have true here, false, false, nope, and let me try again, and false. With the AND operator, the only way we get truth is if both P and Q are true. So now let's negate it. So the negation, P and Q, well, that's just going to flip all of these. So we would get false, true, true, true. Now let's do another thing. Not P or not Q. That's a little bit tedious, but we can get through this one. Not P or not Q. So two things are happening at once here. We have to flip the assignment on P. This flips to false. Flip the assignment on Q. That flips to false. Because it's an or operator, that would make the whole thing false right here. Then we do it again. Let's be really careful with the next ones. It's not P, but P is true, so it's become false, or not Q. But Q is false, so that turned to true. So flip these around, false, true. Across an or, you would get true. Does that make sense so far to folks on getting these first two assignments? Okay, let's keep on going to the next then. So for not P on row 3, that one's true. For not Q, that's false. Again, imagine these flipped, but because this flips to true, we would get true here as well. And then one last time. But this one's a little bit easier to see. If it's not P and not Q, but both of these are false, this is a true statement or a true statement being connected. So we would get true down here. And now notice what's happened with our assignments. There's a match on all of the statements for true to false, false to true. And if that's the case, that shows we have actual logical equivalence right here. A lot of different ways you can say this. We could say that the statement here, the statement on the left, is a tautology. If this one's true, this one is true. If it's false, this one is false. They're really saying the same exact thing, in other words. And there's lots of other kinds of things like this we want to check out as well. But this is the other value of the truth table. The reason we were writing them down so much, it becomes a pretty interesting tool for this kind of logical computation or verification we saw here. But at this point, I'm kind of stretching for material. This is stuff we're going to take a look at in section 3.3. So I'll turn it back over to the class. Any last questions at all, folks, before we call it a night? Okay, well, if you do have questions, I'm pretty much here until my next class at 7:30 anyways, so feel free to stick around. Otherwise, we'll come back on Monday's class, get through our exam. A week away from today, we'll be in section 3.3, seeing where all this is going. We'll be looking at more tables like these. The other really big thing that we haven't discussed is the quantifiers. The universal quantifiers, the existential quantifiers are another thing that makes logic kind of an interesting thing to break down when you see it the first time. So section 3.3, a week away from today, pretty good section to take a preview of before we get started on it. But have a great weekend, folks. If you have any questions, I'll be very happy to help out. Otherwise, I'll see you all later.
Thank you,
Thank you.
Professor.
Yep, take care.